Graded potentials and action potentials. So in this lecture, we're going to do a little bit of alternating in talking about a concept and then a process, and then back to a concept for a while, and then back to a process for a while. So concept. On any given neuron, there's a variety of stimulus receptors. Remember all of your dendrites on the multipolar neuron, that receptive field? Those are your stimulus receptors. Any given axon terminal is capable of releasing one of a variety of neurotransmitters. The neurotransmitter movement through the synapse takes about 5 milliseconds. We'll find out later that this is the limiting factor in signal transmission speed, this chemical movement across that short distance. Stimulus receptors, which are at the receptive end, receptors are going to be at the receptive end, may be opened directly by mechanical stimulation, if they're mechanoreceptors, changes to sensory input like light, or chemical binding to receptors, like if a receptive end of a neuron gets bound by a neurotransmitter. You may have ligand-gated channels that will open up in response to that chemical bond. So for the time being, we're going to be talking about the soma and dendrite end of the neuron. The receptive end of the neuron is the plasma membrane of the cell body of the soma and the plasma membrane of the dendrites. Both the dendrites and the cell body are studded with those ATP-driven sodium-potassium pumps I was talking about, sodium, potassium, and chloride leak channels, and stimulus receptors. So receptors that are there to, in most cases that we're talking about, that are waiting to be bound by a neurotransmitter to open and do work. The opening of stimulus receptors lets sodium in and potassium out. So they open and allow the flow of ions. This causes a small change in the membrane potential at that site. So you have, here's an axon terminal. You release neurotransmitter or whatever. It binds to a channel that is opened by that neurotransmitter. It lets sodium in. Remember, you've been spending energy to pump sodium out. It lets sodium in and potassium out. This is going to help bring closer to equal the balance of charges across that membrane. You are constantly, before spending energy, to maintain a certain resting membrane potential. You are keeping it polarized. Opening that channel leads to slight depolarization. Those channels open and close super fast. This small, local, fleeting depolarization will spread energetically. Let me erase this a little bit. In all directions. Now, there's lots of leak channels here too. And you've got your sodium potassium pumps. So this energy, this influx of sodium doesn't last very long. The energy created, or the potential created, or sorry, the energy created by this shift in ions is going to go away pretty fast because of those pumps and leak channels. Each one of these events, these small, fleeting depolarization events, are graded potentials. They're stimulus driven. The greater the change of the membrane potential at that site is going to be relative to the stimulus it received. The adding up of these graded potentials, these small, fleeting, very localized depolarization events, the adding up of those is going to ultimately, hopefully turn into an action potential if you have enough of them. We'll get into that in a bit. Neurotransmitters, when they bind to a receptor, are going to open up that channel and allow a movement of ions. Depending on what type of neurotransmitter that is, the neurotransmitter may stimulate either an excitatory response or an inhibitory response. You're constantly maintaining a resting membrane potential of minus 70 millivolts. Remember that volts refers to potential, and the inside of the cell is, relatively speaking, negative compared to the outside of the cell. That's why there's the negative there. And 70 refers to the imbalance of 3 sodiums on the outside and 2 potassiums on the inside. That's what it ends up basically balancing out as, is 70 millivolts difference, more negative on the inside, so minus 70. If the neurotransmitter released is excitatory, the stimulus received will incrementally depolarize the receptive end of the membrane potential, or the receptive end membrane potential. So depolarization would be represented by a shrinking of this number. Remember, this refers to the difference. The 70 refers to the difference. 0 would be no difference. So an excitatory neurotransmitter might open up a channel that'll allow enough of an ion shift to maybe bring that to minus 60. If you keep blasting that channel and nearby channels with more excitatory neurons or neurotransmitters, you might bring it up to minus 50 or minus 40 or whatever, closer and closer and closer to depolarization, until the membrane is so depolarized that it stimulates an all or nothing electrical zap called an action potential. Mechanism about that will be talked about later. Either way, what we're talking about is excitatory neurotransmitters will change the membrane potential on the receptive end of the cell and bring it closer and closer and closer to that all or nothing electrical zap. Inhibitory is exactly the opposite. It's going to cause a shift in ions that brings you further away from being able to give an electrical zap. So here's your threshold. Once you've had enough excitatory neurotransmitters hitting, now you can fire off your stimulus. An inhibitory neurotransmitter will bring you further away, so it'll bring you down to like minus 80, minus 90, minus 100, whatever. Not always in these even increments, it's just good illustration. Further and further and further away, so that to get it up to threshold is going to require a huge amount of excitatory neurotransmitter input. It's going to make it harder for the downstream neuron to fire. So the excitatory and inhibitory neurotransmitters are the chemicals that bring the downstream neuron either closer to firing off an electrical impulse or further away from being able to do that. The excitatory postsynaptic potential is that graded potential created by the binding of the neurotransmitter. Inhibitory postsynaptic potential is the graded potential created by the binding of that inhibitory neurotransmitter. The more stimuli the receptive end of a neuron receives, the greater the effect of that stimulus. These summate in a similar way to muscle fibers summating with their signals. There's two major types of summation that a neuron can experience: spatial and temporal summation. They're a little bit more straightforward than they might at a glance seem. Spatial summation means you're firing a lot of local transmitter across a lot of space. You're firing a lot of neurotransmitter across a broad area of the plasma membrane. Spatial, like space, it's spread out. You've got a lot going on overall, a lot of the membrane. Temporal summation is where you're blasting that neurotransmitter really fast or a lot. You've secreted a lot in a certain space that the receptors on the downstream neuron are just, as soon as they get a chance to close back up again, they're getting open again. And so you're depolarizing at a specific site an awful lot. For the purposes of our lecture, we're going to assume that the neurotransmitter released is excitatory, unless I say otherwise. So far, up here, you have ligand gated channels, mechanically gated channels as well, and you have those pumps and leak channels, right? You don't have any voltage gated channels in the dendrites or the soma. Those show up at the axon hillock, this cone or funnel shaped part where the cell body pinches down and becomes the axon. Those are only open and closed by changes in the membrane potential. So you have neurotransmitter being released. Oops, that's white. At a ligand-gated channel on a dendrite. That ligand-gated channel will open up in response to the neurotransmitter binding, provided it's X, and it will depolarize that little area slightly and quickly, and it'll go back to being completely depolarized again soon. The resting membrane potential before any neurotransmitter binds to that spot around that receptor is 70, minus 70 millivolts. When you have that neurotransmitter bind, if it's excitatory, it'll bring that membrane potential to a smaller number, closer to 0. 0 would be complete depolarization. Everything is equal when it is no longer polarized, when it is depolarized. So maybe it'll bring it down to 69. And then another neurotransmitter binds and it comes down to 68. And then another one right after that and it brings it down to 67. These differences in charges over a space, or how quickly this happens, will add up basically and spread out a little bit through the plasma membrane. Once a strong enough of a signal hits the axon hillock, different voltage gated channels will open or close based on the change in charges. If a voltage gated channel in the axon hillock, if the plasma membrane at the axon hillock gets to minus 55 millivolts, there's been so much depolarization happening with neurotransmitters binding that you've brought down the depolarization from minus 70 to minus 55, your sodium gated channels will open and allow sodium to rush back into the cell. If you bring it to 30, if you overshoot depolarization by moving sodium a little too long, so to speak, those sodium gated channels will close and potassium channels will open. That will keep going until you overshoot resting membrane potential and go all the way up to minus 85. From here on, unless otherwise stated, sodium channels and potassium channels are going to refer to those voltage gated channels. So again, each graded potential represents a small limited change in membrane potential in how polarized that membrane is at any given place. It's a very small limited change. But remember, the soma has a lot of plasma membrane and a cajillion dendrites that are all making a cajillion connections. You can have this little tiny phenomenon happen thousands and thousands of times at the same time at any given time. If enough happen at once of a particular stimulus, and each one ends up being strong enough, then the membrane potential overall will build up so that all the way down here, far away from the dendrites, even there, you have an imbalance of ions compared to what the resting membrane potential likes to be. If you've had so many of those little tiny graded depolarization events that the membrane voltage here at the axon hillock goes all the way from -70 to -55, those sodium channels will open, and your action potential, which is an all or nothing, unstoppable, non-lessening electrical signal, this will be stimulated and the process will be started to shoot that electrical signal down the axon. The opening of those sodium-gated channels when the membrane voltage potential, that should be -55, at the axon hillock reaches -55 millivolts, is the initiation of an action potential. So this would be a good time to pause and go to the video that I've posted also in this folder of how dendritic stimulation causes an action potential, how all these little graded events can add up to make a big electrical zap. This guy draws it all out on chalk. He frankly does it a lot better than I can. So I recommend you stop now, go take a look at that, and then pick up on the next slide where we've left off. So let's lay down some action potential rules before we move forward. Action potentials are all or nothing. They fire completely or not at all. Depolarization at one site will set off depolarization at another downstream site on the axolemma. At the same time, when you have those channels starting to reset and try to go back to normal, the electrical signal can't affect those channels, and it's forcing the signal to go one direction. Once an action potential starts, it cannot be stopped. So you either fire it completely and it goes 100% to completion, or you don't fire it off at all. They're unidirectional, as we mentioned, and they are irreversible. Again, once you've started it, you can't stop it, you can't turn it backwards, and you can't undo it. Okay, so now we have our graded potentials. They've been coming in fast and furious with neurotransmitters binding on the dendrites, on the soma cell body, and that's been happening so much that the overall plasma membrane voltage, transmembrane voltage, has gone from -70 millivolts to -55, as far away from all that stuff as the axon hillock. This represents a pretty big, a lot of things happening to make that kind of a change. So at the axon hillock, you have those sodium voltage gated channels. Those open when the transmembrane voltage gets to -55 millivolts. Since that threshold stimulus has been met, they're going to open up. And at this point, sodium is going to rush into the cell. Those sodium voltage gated channels don't close until a different voltage is met, +30 millivolts, meaning the inside of the cell is 30 millivolts higher, more positive, than the outside of the cell. So the positiveness used to be on the outside, and it was quite positive because the inside of the cell was negative. And now so much sodium has rushed in that the inside of the cell isn't relatively negative, it's now relatively positive by 30. You can think of -55 and +30 as being an on-off switch. When the threshold voltage is met, when the voltage around the sodium voltage gated channels hits -55 millivolts, the on switch is turned and the channels open. When sodium has rushed in so much that the inside of the cell at that spot hits positive 30 millivolts, the sodium channels turn off. Minus 55 on, positive 30 off. So 3 things happen. First of all, after all that rushed in, the sodium channels close, and you have sufficient depolarization to set off the next downstream sodium channels. Because you're not polarized the way the cell normally is, right? You have this whole normal, or like this whole wackadoo different voltage going on that's higher than minus 55. So the downstream sodium channels are going to open. More sodium's going to rush in. Once it hits positive 30, it's going to close. Then the downstream ones are going to open, and then the ones down from that, and the ones down from that, and the ones down from that. And as such, whenever you have a movement downstream of these opening and closing of voltage-gated channels, that represents and is the result of an electrical signal getting transmitted down the length of the axon. Now, another thing is happening. At that positive 30 millivolts, turns out that that's the on switch voltage for potassium channels to open. This whole process, you have enough graded potentials added up to hit threshold voltage at the axon hillock. Sodium channels open, sodium rushes in, sodium channels close, potassium channels open. Signal gets transmitted to the next downstream channels. That takes a millisecond. It's a super fast process. And whatever is happening, the next thing in line that's going to be affected is whatever the next door channel that's available to participate in this ion exchange is. If it's super close, then that energy will go close by, and it'll go in little steps. If it's far away, it'll still go to whatever the next one closest is, even if it's far away. It'll happen with the same all or nothing oomph, and the signal will get to go faster because it'll get to make bigger jumps for each millisecond it takes to transfer that signal downstream. So your sodium channels opened up, you had a bunch of sodium rush into the cell, now you are depolarized. You have actually passed depolarization a little bit so that the inside's actually a little bit positive. You didn't get to 0, you overshot that a little bit. At that positive 30, your potassium channels open and sodium channels close up. Now, this process is the beginning of putting the charges back to where they originally were so that this section can fire again. You can't go back and fire another action potential in that spot until the stage has been set to how it was in the beginning. So the potassium voltage gated channels are going to open up and potassium is going to rush out. The cell will repolarize. The closing of the potassium channels happens at minus 85. That's more polarized than the cell was in the beginning. So when you depolarize, it's like, whoa, you rush a bunch of stuff in and then you overshoot it. And then you have the potassium channels open and whoa, stuff's going to rush out and then you're going to overshoot it. And then you got to get back to normal. So you had depolarization with sodium rushing in. You have the process of repolarization happening when you're letting potassium out to put the outside to try to get the outside to be more positive. And since those are kind of slow to close up, they're slow to act, you'll end up overshooting that minus 70 mark before the potassium channels get to be shut. And now the membrane voltage is minus 85. The inside of the cell is 85 millivolts less than the outside, basically, in charge. This difference between the minus 85 and while the cell starts to burn some energy to get back to that minus 70 is called hyperpolar. What's hyperpolarized when it's at minus 75, and the whole time it's taking to get back to minus 70 is a hyperpolarization period. Repolarization plus hyperpolarization takes about 3 milliseconds. So the firing of the action potential itself is super fast. Getting yourself back to normal takes a little more time. Now, since the next downstream potassium channel has already opened after that 1 millisecond, and that last set of channels has already started the process of repolarization and hyperpolarization, they're still like in a weird, positive, putting things back to normal place. They can't fire another action potential again. They're still in a place where the inside of the cell around those channels is a little more positive than outside. You can't fire an action potential like that. You need the action potential to be like negative 55. So the signal can't go backwards. You can't fire an action potential backwards. You can only fire it downstream in one direction towards the axon terminals. All of this is starting at the axon hillock, and it can only move in the direction of the action terminals. This guarantees unidirectional flow. And every voltage-gated channel is going to participate in the provocation of this all or nothing response. And since every channel is an all or nothing event, the entire signal is going to be all or nothing, and that there will not need to be any, it effectively gets like reboosted between channels so that there's never any signal loss, however far that action potential has to travel, however long that axon is. The information delivered at the end packs as much of a punch as the cell got in the first place. So that period between the minus 85 while the cell's trying to get back to minus 70, all that's really happening there is the cell's going back to its usual membrane potential maintaining stuff. You've got your sodium, potassium, ATP powered channels working again, pushing out 3 sodiums for every 2 potassiums in. You've got your regular sodium leak channels, your regular potassium leak channels. These ones that I'm talking about right in this moment are not the voltage gated channels. They're the regular leak channels. You got your chloride channels operating. It's the regular stuff. And eventually, when those have been working for a little bit, the membrane voltage will get back to normal. So this video I will also include in a link on Blackboard. It doesn't show up here, obviously, you can see that, but it will show up in a separate item object on in the folder on Blackboard that will hopefully help illustrate this process so that you can get a good visual, a 3-dimensional visual of why the signal can only travel in one direction and why it's an all or nothing process. So the action potential is going to continue down the length of the axonlemma. This is all happening across that membrane of the axonlemma. Remember, when things are happening, it's probably across some kind of a membrane. In this case, it's the plasma membrane of the neuron, of the axon of the neuron. It's going to continue down the length of the axonlemma until it reaches the axon terminal. Those are the end splayy things that spit out neurotransmitters for other stuff to pick up. The overall conduction velocity varies based on a few things. How far apart the channels are that can participate in this process. Remember, if they're really close together, the signal will transmit all or nothing to each one, but each hop is pretty short. If they're further apart, each hop is long, and each hop takes the same amount of time, whether it's close by or far away. So by spacing your channels out that can participate in this process far away, you can make the signal go faster. Myelin basically works by doing this. You have ion channels down the length of the axon, but where you have myelin, whatever ion channels you might have that could participate can't. Because the myelin, remember, is a plasma membrane with nothing else in it that wraps around itself over and over and over and over and over. That plasma membrane doesn't really have any channels of its own. It's just going to block whatever else is going on. So only between myelinated segments at places called the node of Ranvier, each one is called a node of Ranvier, the signal will jump between each of those. And you'll have these nice big hops that help the signal go really fast. In addition, large axons conduct faster because there's less resistance. The internal stuff in the axon confers some resistance. The smaller that axon is, the more the cytoskeletal architecture, the organelles and stuff are in there, are pretty packed in. And all of this has to happen in fluids, right? You don't want stuff in the way. So the bigger the axon, the less resistance there is. Now, the action potential will continue down the length of the axonlemma, either, hopefully, if the axon's myelinated, which most of the ones that we're talking about are, It's going to hop from node of Ranvier to node of Ranvier to node of Ranvier, all the way down until it gets to the axon terminal. At that point, that action potential will open up calcium channels, voltage-gated calcium channels, that are going to allow calcium to rush into the cell at the axon terminal. At that point, the calcium does what? Remember back to the muscle physiology lectures. This is that first part of muscle contraction and excitation-contraction coupling. The zap comes down the axon, the action potential rushes down the axon until you reach the end of the axon where it's branching off into axon terminals. That zap opens up calcium channels, voltage-gated calcium channels. Calcium rushes in. When calcium rushes in, it signals to the axon terminals, hey, you know all the neurotransmitters that are hanging out here? Bundle them up in vesicles and get them out. You exocytose your vesicles of neurotransmitter. Maybe it's ACH, like we were talking about with muscle fibers. Maybe it's something else. Maybe it's dopamine or GABA or whatever. That's going to diffuse across the synaptic cleft. It's going to bind to that postsynaptic receptor, and it'll do something to the downstream cell. It's the same process we were talking about with the muscle fiber. Only with this, it's not necessarily a muscle fiber at the other end of that neuron, at the other end of that synaptic cleft. It could be another neuron. It could be it could be a receptor on a gland. It could be something else. It's not necessarily a muscle fiber. But this whole process from that axon terminal part through the synaptic cleft part is all the same as you learned with the muscles. A quick note about those neurotransmitters. They don't just stay bound to that downstream, that postsynaptic receptor forever, right? It's not like once you fire a neuron, the next neuron is going to get super stimulated and then never going to be able to fire again because it's drowning in neurotransmitters. They pop off. So the neurotransmitters bind momentarily, and when the shape of the receptor changes to do its thing, the neurotransmitter will get kicked off. And a few things can happen with the neurotransmitter. They might just diffuse away into extracellular space. Astrocytes will then suck them up and try to recycle them and give them back to other neurons. They may be they may just drift off completely and reside in the extracellular space for a while. They might be taken back up by that axon terminal and get used directly in that moment. And they might just get degraded by enzymes. One of those is the fate of basically all of your neurotransmitters. You might have heard of drugs called reuptake inhibitors, like the psychiatric medicine SSRI, selective serotonin reuptake inhibitor. What that's doing is you release the neurotransmitter serotonin from the axon terminal. It binds to the downstream receptor, the postsynaptic receptor, and then ordinarily it pops off. And sometimes it gets retaken back up into the axon terminal for reuse. This is a little bit of a slow process, and it makes it so that you don't have any more neurotransmitter in the space in the synaptic cleft than you absolutely need. But sometimes, for some of us, that process happens a little too quickly, or the axon terminal holds on to serotonin a little too long, or it doesn't secrete very much in the first place. And so you don't have very much stimulus going on the downstream, the postsynaptic cell. So by giving somebody a reuptake inhibitor, an SSRI, a selective serotonin reuptake inhibitor, what you're doing is preventing the axon terminal from getting that serotonin back so that it can build up in the synaptic cleft and properly stimulate the postsynaptic neuron. For problems that are affected by not secreting or hanging on to enough serotonin, by giving somebody this drug, allowing the serotonin to build up in that space can cause a more normal feeling physiological state for your patient.